Hey, Dr. Cluck coming back at you with another differential equations video. We're in section 8.2, and we've got a check your understanding problem here. It looks like they've given us a homogeneous linear system right here, plus initial condition, so we've got an initial value problem. And they want us to write the system as a matrix vector problem and then use the eigenvalue eigenvector method in order to find the solution. So let's jump right in. Part A, if we let the vector y equal xy, then we can write this differential equation here as the derivative of vector y would equal the matrix 5, 2, negative 2, 1 multiplied by the vector y, and the initial condition, y of 0, is the vector 3, 1. Okay, so the initial conditions are xy equals 3, 1, so if x and y are here and here, then that's the 3, 1 initial conditions. And since this is 5x plus 2y here, we get 5x plus 2y by doing row times column in the multiplication, and negative 2, 1 here, negative 2, 1 times xy gives you negative 2x plus y. So that is writing the problem as a matrix vector problem. And then for part B, we're going to need to know the eigenvalues and eigenvectors of this matrix, and that will allow us to construct the solution. So to find the eigenvalues, we take the determinant of of this matrix minus the lambda I matrix. So if maybe I'll just write out the details. We're looking at the determinant of A minus lambda times the identity matrix, where A is this matrix right here. So that's 5 minus lambda, 2, negative 2, 1 minus lambda. When we take the determinant, we just take the product of the diagonals and subtract them. So I get 5 minus lambda times 1 minus lambda here, and then we subtract this way, and negative 2 times 2 is negative 4. So when I subtract negative 4, I get a plus 4, and we set that equal to 0. So this is lambda squared minus lambda minus 5 lambda plus 5 plus 4. So that would be what? Lambda squared minus 6 lambda plus 9. And it looks like I can factor that into lambda minus 3, lambda minus 3. So lambda 1 is equal to 3 and lambda 2 is equal to 3. We have a double root in our system. Okay? And when we have a double root, then the solution, normally our solution method would just be C1 e to the lambda 1 t vector 1 plus C2 e to the lambda 2 t v2. But since we have a double root, we're not going to have two linearly independent eigenvectors here. And so this is not going to work. Okay, so that's not going to work. So what we do instead is we use an alternative solution method, which is to say y of t is basically the initial condition, which in this case is 3, 1, times e to the lambda t, plus t e to the 3t times another vector, which for now I'm just going to call v1. Okay, so this sometimes we call v0, which is basically that initial condition they gave us. v1, the definition of v1 is it's the A minus lambda I matrix multiplied by the initial condition. Okay, and in this case, the A matrix is 5, 2, negative 2, 1. 5, 2, negative 2, 1. The lambda I matrix would be 3, 0, 0, 3. And then the initial condition vector is 3, 1. And so this will give us what? 2, 2, negative 2, negative 2, multiplied by the initial condition vector, and that gives us, what? 8, negative 8, I guess. 8, negative 8. And so we can put in 8, negative 8 right here. And that will be the final answer to this problem. Okay, so if you were looking for the general solution, then you could just put, C1, C2 here, and then do the same process, and then your answer for V0 would be C1, C2. V1 would still be equal to whatever, 2, 2, negative 2, 2 times C1, C2 is. It would give you sort of an answer in terms of C1 and C2. So you can still get the general solution this way, but if they give you the initial condition, this works fairly well. Yeah. So just to kind of point out what would happen, if you had put this into Wolfram alpha and asked it for the eigenvalues, you see you're only getting the 3 and then the negative 1, 1 as the eigenvector. Or I guess you could call this 1, negative 1. And what's interesting is you can see here, this 8, negative 8, that's a multiple of 1, negative 1, that eigenvector. So this process usually gives you, this will end up being in the direction of the eigenvector, and this will be in the direction of the initial condition. Okay, but I believe that's what they wanted us to do. We found the solution to the initial value problem. It is right there, and we'll leave it at that. So hopefully you got that problem right, and you're understanding how to solve problems with double roots. If not, do some other practice problems, and we'll see you in the next video.